Just to say again, what do we have? We've got a circle and a set of n distinguished positions. Okay? And we've got all the n square varieties of strings, which are labeled by which of these positions they begin on and which of them they end. Okay? Suppose we're in the generic situation where all these crosses are distinct. They don't line up. Then you can ask, how many massless nodes do you have? And the answer is clear. Any string that stretches between here and here will have some mass. Just like a winding string has mass. The mass will depend on the difference between these positions. There will be mass. However, strings that go from here to here will be massless. And it could be massless, and in particular have the same spectrum as our usual massless spectrum. Okay? In particular, there will be no massless gate goes on going from here to here, but there will be a massless gate goes on going from here to here. So the effective massless spectrum of the theory is U1 to power n. That's the same as in the original theory. See, the Wilson line is an adjoint field which hits down the theory from un to u1 to the power n. As we've seen in the spectrum computation. We don't have states and outcomes in say un multiplets of different masses. Okay? But in the stereo picture, the whole thing is very pictorial. The n abstract Champeyton indices of the original theory become n distinct locations. The n squared flavors, abstract flavors of strings in the original theory, become just labeled by where they start and where they end. N values for the first, n values for the second. Okay? These different hypersurfaces here are called diploids. And we've already seen many things. If you think about it, we've already learned many things. We've learned firstly that there are states in string theory which include diploids. How have we learned that? We've learned that because, well, assuming that there are open strings, that open string theory is consistent. States with diploids are just on a circle. States with diploids are just different description.
It is not clear that there is different description.
No, it's not. I think it is. It's just a field redefinition of the word. Yeah, it's XL goes to XL, XL goes to minus XL.
Okay, which was something that we could do there. We saw that. There the argument involved something like going to the circular radius and arguing that these are just two gauge equivalent things, and hence these two descriptions are the gauge equivalent. But how does the argument go in this case?
Well, there are two questions you might be asking. The first question is just a classical string theory. Okay? And the second question is non-perturbative. Okay? And the level of classical string theory is just a reformulation. You change the variables on the sigma. Okay, so there's this one question. Okay, now non-perturbatively, I think basically what you would have to assume, you see, basically what will be going on is the following. If you think of the open string theory as some state in the background of the closed string, okay, then anything that's related by gauge transformations of that state that we get by gauge transforming that state, okay, will also be an equivalent state. I mean, now this part of course is more philosophical. But please go.
The argument that the triviality is a gauge transformation in the closed string sector.
Yes. And that the open string theory represents a state. Is the theory that you get out fluctuating around a particular state of the closed string. The thing that we talked about. Okay? So,
Which we are not seeing anyway in this.
we're not seeing it. Yeah, except for its boundary statements. Okay? But now this bit gets a little philosophical. Okay, so, like I said, it's not as explicit. But assuming that is the case, okay, then whatever description you get by acting on that state by a gauge transformation is equivalent, right? Gauge equivalent to the initial state. But what you get by acting on the state which was,
it is in principle possible that triviality was only a gauge transformation only in the pure closed string. And as soon as you add open strings, it is no more a gauge transformation. And it's no more a gauging.
well, it's in principle possible. You see, if it's the case that the object that you're describing, the open string theory describes fluctuations about a state in the closed string. About a solution to the equations of motion of closed string. And that closed string theory had the original. So that,
But in which theory? In a theory which just contains closed strings or in a theory with both closed strings?
so only closed strings. See, that's what I've been trying to say. This whole boundary state business tells you that there is a state of closed string theory expanding around which your fluctuations include open strings and closed strings. That's what that diagram is. This diagram represents fields of only closed strings.
But
It's not there when
if that is true, okay.
if that's true, you agree. And this boundary state business, at least,
But if I'm in a pure closed string case,
yes.
where is the boundary?
What you see is that having open strings is equivalent to having a particular state of closed strings.
Yeah, but that is in a theory where with both closed strings and open strings to start.
Yes, but you reinterpret every calculation involving open strings as a calculation involving only closed strings, including exchange between particular states. You say these two things are mathematically identical. See, let's look at the cylinder diagram. Okay?
As CF3s, they are very different CF3s. One has a boundary, one doesn't.
They're definitely different. See, at the level of CFT, okay, just classical string theory, the question you asked about the duality is just, analyzable and it's true. Okay? So at that level, we have an answer to your question.
But it just says that,
see, the CFT gives you the equations of small fluctuations about a vacuum. Okay? So if you have two different backgrounds in the same theory, you will get two different CFTs. They are different CFTs and they should be. Okay?
Conversely, the CFTs are the same.
The backgrounds are the same.
Those backgrounds should be.
They may not look the same, but they're the same. Okay? So that you get two different CFTs is fine as that should be. It's not in contradiction with the statement, that having the open strings is doing physics about a particular state of closed strings. Of the closed string. Okay? Now the evidence for this fact is a bit there are many, I don't want to overstate this, because the normalizability problems are what I say. See, I have to discuss this boundary states with you. And the boundary state is formally a state in the closed string sector, but it's not a normalized. I don't want to, basically, let's not get into that too much, except we have to discuss that honestly before. But let me just tell you again that the evidence is this. If you take let's look at the cylinder. Okay? The cylinder amplitude which contributes to the vacuum energy of open string theory is the same contribution you will get if you were working with only closed strings, but in a particular state of the closed string. Okay. This is the reason at this point. We'll see more reasons as we go on. Basically you can say that the G-brain is a soliton of closed string. And we'll see this. We'll see more evidence built up for the statement as well. Okay?
How many we can't see solitons at least in this thing. So, there's nothing inconsistent with what it is.
Please go on.
How do we know that there's something? We just get the soliton solution which you quantize. You should be these things.
Yes, and we solve the low energy equations of motion. We find solutions, and we find that they're zero, as you say, zero moles if the massless moles here.
And the actions would go inversely as
it will go like 1 over G, which will agree with this. All of that's going to work out, but let's postpone that for when we get to it. Okay, this is basically the questions you're asking at the heart. The questions that are at the heart, basically, of the Mulder-Sena. You see, Mulder-Sena duality is really the idea that there are two different descriptions of the same system. The first viewed as a state in a closed string, and fluctuations in background, a particular closed string background. Okay? And the second viewed including open strings, and these two are exactly the same. Okay? These are good and deep questions. Okay? But if you accept the state, you see, it's very hard to be totally sure because string theory is not done at that level of precision. We don't have a basic definition. If you ask a question about conformal field theory, those are very precise questions which you can just answer. If you're going to ask a question like non-perturbativity and so on, there will be assumptions involved. Okay? The kind of assumptions that are going in are the assumptions that I've just mentioned. Okay? But assuming that it's true.
It is so clear that it's so easy to do in the bosonic case.
In the bosonic case, yes. You see, we shouldn't even talk about non-perturbativity in the bosonic case. Because the bosonic theory does not, at least it's not clear that it exists. You do a one-loop diagram that doesn't exist. So any statement about non-perturbativity should be interpreted as when we get to the superstring theory. So at the moment, if you want to take a minimalist point of view, the only statements you should take seriously are the trivial statements. Which are then just simple statements of a conformal field theory, which should be directly verified. Okay? But these statements in the context of the superstring will be believed to be more than trivial statements. Is this clear? Okay? But perhaps you want to confine yourself at the moment to just thinking about conformal. Okay. At that level, there's no question. These two things are just the same theory.
But there is some evidence in the bosonic theory that there's something like this which is happening.
What? Like what is it?
That you would have a vacuum like that because in one sense we don't even know what is a virtual vacuum, right?
Yeah.
So.
Yeah, in the bosonic theory, there are many things we have. If you remember, just the open string theory was not a good vacuum. it didn't cancel it out. Didn't have zero vacuum energy. Do you remember that was a problem? So there are many things here that one shouldn't take too seriously. Okay, so nothing I've said. My starting point, maybe just open strings, is an inconsistent sign. Okay, so which won't be the case, when we do things. Actually, that we can cure by adding an orient before. That's what we do. I thought next class maybe postpone further in the future. But anyway, that we can cure. But saying what? No, you see, anything we do will suffer from the tachyon. So if by vacuum, at least you mean stable vacuum. Certainly not. But even, in order to ask, even if it's locally stable, even to ask, to start doing loops around this theory, how do you do it? Right? You've got this unstable direction which always gives you. So any statement in the bosonic theory, it should be taken as just, technical statement that will generalize.
So to understand right that we can't make any.
No, classically, there's no problem with bosonic theory.
Okay.
So any statement of conformity theory is precise.
Then we can't make any good non-conservative statement?
But definitely, that's definitely true. Probably this theory does not exist. Yeah, absolutely, yes. Okay, good. Any other questions or comments? Well, we should stop. We'll stop in 5 minutes. Let me just wrap it up. Okay, but where were we? So we've got this picture of these hyperplanes, and I wanted to say that you see, it's true when we get to the superstring and so on, but we're forced to take these configuration seriously, because if we did start with a configuration that we knew was a good solution of string theory, and we perform a symmetry operation on it, and we land up with another configuration, the second configuration is also a good configuration in string theory. Right? Now, of course, so far we've concluded that D-planes exist in circles. But we could take the R goes to 0 limit of the original theory. That would send R to infinity in the TDU description. And we would effectively have D-planes on a space that's as large as we want. Okay? So presumably then they exist in non-compact spaces. You can just take the limit R goes to infinity in the new description. Okay? What can stop that from being a good solution? So we've concluded. Okay? And of course, now just at the level of conformal field theory, without any of this duality business, we can just study open string theory with the boundary condition delta over x to 0. And that's as good in open string theory as open string theory with del sigma x. So at the level of conformal theory, we didn't need all this duality. This is where we didn't need circles, we didn't need duality. This is a way of telling us that these objects are natural to study. They will appear as configurations naturally, but just at the mathematical level, we could have started without this, just by studying the boundary condition delta of x. Okay? So we discovered a new set of objects, new set of solutions to the equation of motion. This set of solutions has objects moving around, hyperplanes in space. Now, okay. What is the dimensionality of these hyperplanes? We've so far looked at things that have codimension 1, because we tedialize to master. But every time we tedialize, another direction will become Dirichlet rather than Neumann. So if we have, the way to think, the modern way of thinking of the open string, original open string theory, is to think of closely theory the presence of D25 planes. 25 happens to be the dimension of space. So they fill all space. Now one D-duality will give us D24 planes that are localized in one dimension. Another D-duality will give us D23 planes localized in yet another dimension, and so on. There's no limit to this, we can go to whatever we want. So in the bosonic string theory, we have T branes of every dimension. If 0 branes, 1 branes, 2 branes, up to 20. Okay. What is the low energy effective action of the world volume? What are these D branes? So far we presented them as distinguished hypersurfaces in space-time on which strings get hit. But remember that the position of these hypersurfaces was governed by a Wilson line, AII. And remember, of course, that the Wilson line is a dynamical field. In string theory, there's a mode corresponding to this Wilson line. Like this. The mode that was x25 minus 1 acting on the vacuum was the mode that corresponded to A25, 25th component of the gauge field. Okay? And we can have solutions in which this has an e to the power kx as long as k squared is 0. Now we've seen that when this e to the power kx is not there, that represents, the constant mode of that represents the position of the ring. So when this thing is slowly there, k is very small, clearly what it will represent is a fluctuation, space-varying position of the brain. Is this clear? Okay? There is a field in the theory, in the original unmeteorized theory, a dynamical field that will take different values at different points, whose zero mode after T-duality represents the position of the brain. So clearly if that field is varying after T-dualizing, we get the position of this brain varying. Okay? So, you should think of the brain not as some passive God-given surface, but as a fluctuating object. Just like suppose you have this rubber band in space and you stretch it. Okay? It's an object. How do you see it's an object? You see it's an object because its position can fluctuate. You hit it, it moves. There's a field governing the motion of this. If you were just these small fluctuations, that's all you'd see. You can also move it lots. You won't see that as much. In the same way, it's clear that there is a field governing the location of the brain. In string theory, it's just this alpha minus 125 in either picture. Because the oscillators don't change it. Up to minus. Okay? So alpha minus 125, that can move around, you can do whatever you want. Okay? So let's say this again. Suppose we start with the description where we have 25 bits. A single 25 bit. What is the low energy effective description of this theory? Okay? On a circle. Okay? Well, we've got an effectively 24 plus 1 dimensional gauge theory, and then a scalar field, which is the Wilson line, a master scalar field, which is the Wilson line. It's a dimensional reduction. Low energy description of physics doesn't change from this description. So once again, in the TDO picture, you should get a 24 plus 1 dimensional gauge theory with a master scalar field. That's what you get. But the interpretation of a master scalar field is instead of being the Wilson line, it's the position of the hypersurface. Okay? Let's say it again. By choosing out one particular location among the various possibilities in the circle, you break translation invariance. So it must be a goldstone mode corresponding to that broken translation invariance. This master scalar field is that goldstone. Small bits corresponding to translations. Okay? In general, if you are dealing with a deep P brain, you will have a P plus 1 dimensional, you will have P plus 1 dimensional gauge fields propagating on this brain. That's clear, right? Because you will have the usual vertex operators. So, from the point of view of vertex operators, the question is whether you have dtx or dnx. Okay? If your x has Neumann boundary conditions, then dnx is 0, so the only vertex operator available to you is dtx. These are vertex operators that correspond to the gauge bosons. So in every direction that you have known boundary conditions, including time, you have a gauge boson. The zero mode of the string is forced to be located on the cycle surface. So you've got a gauge theory propagating on the brain. In addition, you've got all the other fields that you get from here. These, from the point of view of the brain, are scalar fields. Okay? And they represent the goldstone modes, which are the positions of the brain in transfer space. The number of Dirichlet directions is the number of directions in which the brain is localized. So the brain can fluctuate in these different directions. Okay? Now, just like the gauge bosons of the original theory were matrices. If you have one brain, it was just one unit. If you have n brains, you have these different gauge bosons going, n squared different gauge bosons, some of which are massive. Notice that if all the d brains come together, all gauge bosons become massless. Okay? So you've got a situation where you've got this very interesting situation. You've got a situation where you've got brains that n different brains that are distinct, different positions, and low energies give you a u1 to the power n. But when the brains all come together, you get a un. Okay? The W bosons are just strings from one to the other. They become massive by the usual Higgs mechanism. What is the usual Higgs mechanism? The usual Higgs mechanism emerges from the fact that just like the gauge bosons, these scalars are also in the adjoint. So every open street field was in the adjoint. Right? Further, the scalars have a potential which is inherited from the potential of Langmuir's theory before T-duality. Remember, the potential for Langmuir's theory before T-duality had f squared in all directions, which includes AI commuted AJ the whole thing squared. Now AI becomes a new scalar field after some normalization. So you get xi commuted xj for the massless field, the whole thing squared. Such a potential. Actually, the minus sign. Okay. Trace this. Okay? So, the theory has adjoint valued scalar fields with such a potential. Now, you can ask, what are the solutions to the equation of motion of a scalar field with such a potential? And the answer to that question is commuting scalars. Okay? As you can easily convince yourself by computing the bearing with respect to xi. It's clear that the variation will leave one commutator there. So if everything commutes its equation of motion is satisfied, you can convince yourself there are no other solutions. Okay? Now commuting scalars can by a Human transformation be made simultaneously diagonal. Okay? So what's going on? And the scalars represent, remember, the positions of the brains. So the most trivial solution to this scalar theory is any diagonal matrix which has the d brains put at any different positions. That, because we've got an adjoint field which is taking this value, Higgses down un to u1 to the power. But there's a special value of the scalar fields where some of the eigenvalues come together. In which, say p of the eigenvalues come together, then un is Higgs down to up times u1 to the power n minus 1. Okay? So, something very interesting is happening. The thing that's interesting was as follows. You see, the field that has the interpretation as being the location of these objects is actually, if there are n objects, is actually an n squared value matrix field. When the objects are far away separated, far in string units, then these n squared different fields, there are n massless guys and the n squared minus n very massive guys. And then you've got n different numbers that represent the different locations of these brains. But when these objects come nearer and nearer together, it becomes increasingly artificial to separate off the off-diagonal modes from the diagonal modes. And then the positions of the brains. There's no clear sense in which you can ask where is the brain located. The question becomes enhanced into a question of a matrix. It becomes a question, what is the gauge invariant data in the matrix of the field phi? And there's n squared piece of information there. Okay? So this is our second indication that string theory sees space-time differently from field theory. Okay? The question of location of objects like the brains becomes a question about a matrix, not number. About n squared rather than n numbers, as you would expect from ordinary configurations. Okay? So this is the heart, this observation is the heart of the existence of non-commutativity in string theory, which we will discuss as we go. Okay? So I mean, just 2 minutes, sorry. So what have we discovered so far? We've discovered that string theory has D-branes. The world volume fields of the D-branes include gauge fields on their world volume and include scalars that describe how these D-branes fluctuate around. Okay? Now, these D-branes carry energy, and in particular source the gravity. Okay? In the next class, we will try to understand what we can about the low energy effective action on the world volume of D-branes, and we'll also compute the tension of the D-branes by analyzing one report. Okay, sorry, we will. Any questions about it? Okay. Okay. So Logan's question is that T-duality maps brains that wrap around circles to map to brains that don't. Okay. So Logan's question is how can that match with the derivatives? I make one circle very big, the other is very small, how can that work? Okay? It's a good question, and let's work it out. The first thing that we have to understand is that the dilaton changes under T-duality. Zero mode of the dilaton. It's not something that I described when we discussed T-duality, but let's quickly derive that. You see, under T-duality, the low energy effective action low energy space-time effective action. Okay? But the low energy space-time effective action has a factor in the closed string sector, has a factor of 1 over g squared. Okay? So, now if we have a description when you've got a circular size R. Okay? So, the low energy effective dilaton. Okay? So, 2 pi r times g squared must be equal to 2 pi r prime times g prime. Is this clear? In order to get the same number behind the low energy effective action. Okay? You can derive this also by studying scattering amplitudes and looking at the zero modes more carefully. The question, what is the vertex of relation between normalization of the vertex object as the code scattering amplitudes? We can do that, and perhaps we will at some point, but this is a cheap way of doing it.
Can I say that the dilaton along the okay.
No, this is just about zero mode in all of space time. Okay? So what we consider is that g prime by g the whole thing squared is equal to r prime by r without square. Okay? let's figure the tension of a D. Okay? The tension of a, let's say that the tension of a Librem in P dimensions is Tp. So whatever it is, we don't know what it is. Okay? We'll calculate it. So we have Tp. Now, this, well, the tension we know is Tp divided by G, because the tension is given by a disk diagram, the one-point function of the graviton of the disk diagram, and such a diagram always comes with a factor of 1 over G, calling the usual G discontinuous. Sorry? The disk diagram is having the Librem. What is the source? The one-point function of the graviton of the presence. Present. Okay? So, on general grounds, it has to be proportional to 1 over G times some Tp, which will be a function only of alpha. Why is it a function only of alpha prime? Because the 1 over G factors are clear over here. Meaning it's 1 over G times some number. And the number can only know about alpha prime, because alpha prime is the only data. You see, the factors of G come just by the factors you put into this calculation. What? Because disk diagrams are weighted by vacuum. The sphere is weighted by 1 by G squared, the disk weighted by 1 by G, the torus weighted by 1. And this comes from a disk diagram. So just okay? So, it's always Tp by G. Now the question is, what is Tp? Now, your observation that the tensions must match tell you that, you say, suppose I take a P plus 1 dimensional brane on a circle of radius r. That has energy T P plus 1 times 2 pi over, let's call it G, this is before technicality. This must be equal to Tp by G prime. But G prime is the value of the electron after G. Okay? So it must be that Tp is equal to G prime by G times 2 pi r. That is Tp plus 1. Now, for consistency, and this was your discomfort, there is something that must depend on r, because tension. It's a tension of an object. But that works, you see, because r prime was alpha prime by r. And the T duality is equal to 2 pi square root alpha prime times T. Right. So what we have found, you see, there's both the consistency check as well as usability. The consistency check is that factors of R. Again, if that been some factor of R, that makes no sense. It wouldn't be an object by itself. Okay? Now that it's worked, this is information. It tells us that, for instance, that P is equal to 1 over 2 pi square root alpha prime to the power P times P0. So the tensions of various P rings are related. But in a very nice and reasonable fashion. Okay? And the question is, what is T0? We'll calculate. From this diagram, look, it's with the correct normalization. So it's actually turns out to be simpler to analyze the annuities because their normalizations are fixed and sit on the graph on the board. We discuss this. Is this clear?
Are you saying that this would work out even if I did the calculation for the response?
We'll do the calculation for 10 minutes. It's not more difficult to do the calculation for one case for another. We find an answer that will be consistent. Good. Any other questions on this? See, so the key qualitative point though about your question is the dilettante changes. It could have worked otherwise. It could have been that something of a very large circle is the same as something arbitrarily large circle is the same as something as arbitrarily small circle, and that these things are just system properties. How could that work? The key point is that also the tension also involves dilettante, and the dilettante changes that in exactly the way the complex itself.
And what happens to these things at the real point? So that one of the SU2s is fixed by the degree.
Right.
The binding SU2 is fixed by the degree.
Yeah. Yes. Well, at some point, I'm not sure what to say. You basically have one rather than two SU2s, okay, in the open strings. That's effectively what happens. It's a dual point and not a notch. There's a place where you have one rather than two SU2s. What's confusing me is that there's a normalization difference between the open string. But yeah, sorry. Let me say this. Yeah. Well, yeah, right. Just
for example, G prime equal to G, what will you?
There are two things you could be trying to do. You could be trying to form SU2s out of open string vertex operators. Okay? Or you could try to form some subset of the closed string SU2s. Now, there's some radius in which you can form an SU2 out of open string vertex operators. But I don't think that's self-dual radius. Just because the dimension formula is different for open strings.
But the closed string, one of the SU2s, while having the SU2 is separated.
That's not totally clear to me. Basically because one of the U1 certificates, the e to the power ikx's. It's a question, you see, sounds right. I'm not. There's something that's making me a little uncomfortable there. It's the fact that these things carry winding, and that all these modes carry both winding and winding. But there's probably some linear combination that does. I can check that. I'm not done with that. I'm not sure. Let's not make this table. Other questions, comments?